My dear students, in the last class we have to discuss even odd permutations and conjugacy of two permutations, and then in this class we have to continue some more examples of a conjugacy of permutations, and then try to discuss some problems on this permutation topic. So let us begin with the example in S5. Pi is equal to, we have a 1 3, this is a disjoint cycle, and theta is equal to, we have a again this is another cycle. So we try to find the theta pi inverse. So first we have to write the theta inverse. Theta inverse can be written as in the form of 2 3 4 1, and then we have to calculating in the form we have to take a pi inverse first. We have to taking the pi of inverse. Pi inverse can be written as you have a 4 5 2, and then you have a 3 1, and then we have to calculating in this form. So we have to writing in this form. So this is pi, you have a pi is equal to this form. So we, clearly we have a pi is equal to, you have a 1 3 and 2 5 4, and then we have to take a composition with the theta, and theta is equal to, you have a 1 4 3 2, and then we have to taking the inverse of this, you have a 4 5 2, and then you have a 3 1. And now we starting from here. So 1, so clearly 1 goes to, you have a 3, and then is 3 goes to, you have a 1 goes to 1, sorry 1 goes to 3, and then here is a 3 goes to 2, and then is a 2 goes to 5. So we have a 1 goes to 5. Now here is a 5 goes to, you have a 4 2, and then is a 2 goes to, you have a 1, and then here 1 goes to, you have a 3. Now we have a 3, and 3 is goes to again 1, and then is 1 goes to, you have as 4, and then 4 is goes to, you have a 2 is equal to 2. Now 2 goes to, you have a 4, and 4 goes to, you have a 3, and then you have a 3 goes to, you have a 1. So clearly we have a 1 5 3 2. So 1 5 3 2 are the conjugacy of a, this we can easily calculate into this form. Similarly, we have to write in this pi 1, pi 4, and pi 3, pi 2. So this is equal to while is equal to 3 2 1. In this form we have to write as a pi 1, pi of 1 is equal to, you have a 3, pi of 4 is equal to, you have a 2, pi of 3, and so on, like into this form we can write. Since pi of 1 is equal to 3, pi of 4 is equal to 2, and then we have to similarly pi of 4 is equal to 2, pi of 3 is equal to 1, pi of 2 is equal to 5. So similarly, clearly this 1 5 3 2 and can be written as a 3 2 5 1. This is are the same by the property. Let and as we take another example in S7, pi is equal to this form, theta is equal to this form, then we have to calculate the pi theta pi inverse. So pi theta pi inverse is equal to, you have a pi of 7, pi 3, pi 5, pi 2, and pi 1. So this means clearly we have to pi of 7. So pi of 7 is equal to 7. So we have a 7. So because you have a here you have a pi of 1 is equal to 3, pi of 2 is equal to 6, pi of 3 is equal to 1, pi of 4 is equal to 4, pi of 5 is equal to 2, pi of 6 is equal to 5, pi of 7 is equal to 7. So we have to apply from this by the theorem. We can simply say that this is the same as this is equal to pi of 7, pi of 3, pi 5, pi 2, and pi 1. Then pi 7 is equal to 7. Now we have a next is a pi 3. Pi 3 is equal to 1. Then you have a 1. Pi 5 is equal to, you have a 2. Then is equal to 2. pi 2 is equal to 6, we have a 6, pi 1 is equal to, we have a 3, and then is equal to clearly. Or other way, in this direction we can start from the 1, so we can say that 1 goes to 3, and then you have to next go to 3, 3 goes to 5, and then 5 goes to, you have a 2, so this is 2, then here we have to 2 goes to, you have a 5, then you have a 5 goes to 2, and then 2 goes to 6, so we have a 6, then we have a 6 goes to, you have again 2, and then 2 goes to, you have a 1, and then 1 goes to, you have a 3. Now here 3 goes to, you have a 1, and then 1 goes to, you have a 7, and 7 goes to, you have a again 7, and now 7 goes to 7, and then 7 goes to 3, and then 3 goes to 1, then the complete cycle is equal to, you have clearly 1, 2, 6, 3, 7. So either we have to calculating in this form, or either we have to calculating by this method, then both are equal to, we getting the same result in this form, because this is the same as a 1 to 6, 7. So now we have to try to discuss some problems of this. We have to discuss this portion of permutations. So we have to just, the first is very trivial. Let pi is equal to this, and theta is equal to, we have a 2 permutations. So write pi, theta, and theta pi as a product of a disjoint cycle. So we have to try to write as a product of a disjoint cycles. So pi can be written as a, we can write this is 1 goes to 2, 2 goes to 3, and 3 goes to 4, and 4 goes to 5, and 5 goes to 1. So this is the 1, 2, 3, 4, 5, and now we have a 6 goes to 7, 7 goes to 8, 6 goes to 7, 7 goes to 8, and 8 again goes to 6. So pi, these are the clearly, these two are cycles are a disjoint. So this means this clearly we have to write into a disjoint. And also the first part is equal to this, and then second part is asking about the write 2 cycles. So 2 cycles is equal to, you have a 1, 5, 1, 4, 1, 3, and 1, 2 for this, and then this for 6, 8, and you have a 6, 7. Similarly for this we have to write as a theta is equal to 1 goes to 1, so we have to omit it, 1 goes to 3, and then 2 goes to, you have a 3, 3 goes to 8, 8 goes to 4, 4 goes to 7, and 2, and then we have a 5 and 6 are there. One permutation is equal to 1 is there. So this is clearly is a disjoint permutations. So these are the disjoint. We can write in the transposition form. This is equal to 2, 7, 2, 4, 2, 8, 2, 3, and this is already in the transposition 5, 6 is there. So these are the, we just write this clearly I just mentioned into this form. Theta can be written as a 1, 2, 6, 6, 7, 8, and then 1, 5, 1, 4, and then in this form, and then we have to similarly for theta we have to write into this form. So now we have to calculate the theta and pi. So I just take a theta and pi, or directly I just explain you here. So this is theta and pi. The theta is pi, 1 goes to 1, here is a 1 goes to 1, so we have to goes to 1 goes to 2, so clearly we have a 1 goes to 2, and here 2 goes to 3, and then you have 3 goes to 4, so this means is equal to 4, 4 goes to 7, 7 goes to 8, to 4 and 8, now 8 goes to 4, and 4 goes to 5, so this is equal to 5, and now 5 goes to 6, and 6 goes to 7, this goes to 7, and then we have a 7 goes to 2, and then 2 goes to 3, so this is equal to 3. Now 3 goes to 8, and 8 goes to 6, so we have to equal to 6. Now 6 goes to 5, and 5 goes to 1, and this is equal to 1. So this is clearly we have a 1, 2, 4, 8, 5, 7, 3, and 6. This is a clearly disjoint cycle, and we have to write the transposition of this clearly 1, 6, 1, 3, and so on, like into this form we write in the cyclic permutations into this form. So, if we have to adding this, we have to just ask the question like this, what is the even or odd permutations. So, we just take this is the clearly is a if you take a this is the length is equal to cycle length is equal to 3. So, this is equal to a even transposition, and this is odd, this is also even permutation odd. So, this is even, so you have to give even. So, this is 1 2 3 4 5 6. So, this is equal to 6 is a even. So, clearly this is a we can say this is a even permutation. And similarly for this is a 2 transportation is already. So, this is equal to we have this. So, this is 1 2 3 4 5. This is odd is even odd. So, this is clearly is equal to, this is a even 2 transposition and 1 is odd. So, this means clearly you have a even into plus odd is equal to you have it odd. So, clearly we have to just say that this is clearly 5. So, this is a even permutation. Now, we have a 8. So, this is 8 is even. So, we have to getting the odd number for 2 cycles. So, we have a this is a 7. 1 2 3 4 5 6 7 and 7 is odd. So, clearly this is a odd permutation. So, now I think this is clear. We move to the next. Write each of the following permutation as a product of a disjoint cycle. Now, clearly this is not a disjoint. So, we have to write this as a disjoint cycle. So, we clearly say that 1 3 4 is not a disjoint. So, we can start from the back side. So, we have to start from the 1 and 1 goes to 3 and 3 goes to 5. Now, we have here is a 5, 5 goes to 5 and 5 goes to 1. So, this is equal to 1. Now, we have to 2 goes to 2 and then we have to write is equal to the form of 2 and 2 goes to we have 2 goes to 2 and 2 goes to 3, 3 goes to 4 and 4 goes to you have a 4 and 4 goes to 4 and then 4 goes to 1 and then 1 goes to 2. So, this is equal to 2 3 4 and you have a 1 and 5 and then clearly you have a all this is this clearly into this form. So, we just say that 1 5 and 2 3 4. So, this is means the disjoint cycle of a this first one is equal to you have a 1 5 and 2 3 4 and this clearly is a disjoint. Now, for the similar this is again this is not a disjoint. So, we can start the second one. So, we just write as a 1 goes to you have a 2 and 2 goes to have a 3 and 3 goes to you have a 2. So, this is equal to 2. Now, 2 goes to you have a 4 and then 4 goes to 4 and again 4 goes to 4. So, you have a 4 and then 4 goes to you have a 6, 6 goes to 6 and 6 goes to 1. So, this is equal to 1. So, you have a 1 2 4. Now, we starting from the 3, next is equal to 3, 3 goes to 3 and 3 goes to 2 and 2 goes to 5. Then we have a 5, 5 goes to 1, 1 goes to 1 and 1 goes to 3. Then we have a another set is equal to 3 5 and now we have to 6. We starting from the terms is not appearing in here. So, this 1 2 3 4 5 and we have to 6. So, we have to start to 6 and 6 goes to 5 and 5 goes to 5 and 5 goes to 6. So, we have 6 is equal to 6 and now we have start all are the this. So, we have a 6. So, with this we can say that there is a we have a disjoint cycle is equal to 1 2 4 3 5 and 6 are the disjoint cycle of this. So, clearly 1 2 4 3 5 and 6 are the second one is a disjoint cycle and similarly for the third one is again not disjoint. So, we can calculating of this third one we have a 1 goes to 4, 4 goes to 4, 4 goes to 4, 4 goes to 4. So, 1 goes to 4, 4 goes to 2, 2 goes to 3, 3 goes to 1. So, this is equal to and 1 goes to 2 and then we have a 2 goes to 1, 1 goes to 1, 1 goes to 3, 3 goes to 3 and 3 goes to 2 and 2 goes to 2 and 2 goes to 1. So, here is a 1 4 2 3 and that is complete the disjoint cycle of a in this case we have a in this case. So, we write all the three problems are the disjoint cycles of these 3, easily we have to calculate in this form if we have a. Another question is find order of each of the following permutations, and now we know that the method of this is length of a cycle is called the permutation is a 2, then is a order of this permutation is equal to 2. 147 is a 3, and then is a order of this equal to 3, and this is we have a k, order of this is equal to k, and this is equal to 1 2 3 4 5, then is equal to cycle of a length is equal to 5. So this is disjoint cycle of a length 5. So this order of this is equal to 1 4 7 6 2 is equal to 5, order of 1 4 7 is equal to 3, order of 1 4 is equal to 2, and order of this a1 up to ak is equal to you have a k. So by the theorem we can simply say that if we have a this is 2 3 5 and k are the order. Now this what is the order of each of the following permutations, then now this is the we can just length is equal to 3, and this is the length is equal to 3. So we take a LCM of 3 comma 3. By the theorem we say that if a length m length n, then take a LCM of a LMN is the order of this permutation of a this disjoint permutation. So this is equal to 3, and now this is equal to we have take a LCM of a 3 comma 4, and then similarly we have to take a LCM of a 3 comma 2, then you have a 6, and then 3 comma 4 is equal to you have a 12, and now we have a right into this. Now this is again is a disjoint, so we have to take a LCM of 3 1 2 3 4 5 6, then you have a 6. So we have again similarly we have to just write as equal to 3 12 6, and then we have again 6. Is not a disjoint. So first we have to write a disjoint cycle of this. So we have to starting from 1. So 1 goes to 1, and then 1 goes to 2. Now 2 goes to 4, 4 goes to 4, and 4 goes to 5, and 5 goes to you have a 4 goes to 5, and 5 goes to 1. So this is here 1 to 4, and then we have to start from the 3, and 3 goes to 3, and then we have 3 goes to 3, and 3 goes to 5, and now 5 goes to you have a 6, and 6 goes to you have a 6, 6 goes to 7, now 7 goes to 7, and 7 goes to 2, and then 2 goes to 3. So another is equal to you have a 3 5 6 7. So we have a complete disjoint cycle of a this is equal to 1 2 4 3 5 6 7. So similarly this is also not a disjoint, so we can make a this cycle is again is a disjoint cycle, and then we try to solve. So this by the theorem this is 6, this is LCM. Now we take a order of this, we take a of this, now this is equal to 3, and this is equal to 4, this again is a 4, and again this is not a disjoint. So we first we make a disjoint 2 5 3. So we can start from the 1 goes to 1, 1 goes to so on, so 1 goes to 1 is finished. So this is one cycle. Now we have the 2 goes to 4, and 4 goes to 5, so 2 goes to 5, 5 goes to 2, and 2 goes to 2, then we have a 2 5 is a one cycle. Then we start from the 3 goes to 3, and 3 goes to 4, and now 4 goes to 5, 5 goes to you have a 3. So the hand again you have a 3 and 4. So there is a this cycle, then is equal to this is LCM of a 2 comma 2 is equal to 2. So we can find easily the order of any disjoint cycles by the that theorem can say that LCM of a length of a cycle of a m and length of cycle is equal to n. And now another question is this: what is the order of product of a pair of a disjoint cycle of a length 6 and 4? So that is again very trivial question. So we can find the order by the using again the theorem, because we have a two disjoint pair is written as a disjoint. So, clearly is a pair of a disjoints. So, one of the length is a 4, another is a length is a 6. So, we have to take a simply is equal to LCM of a 4 and 6, and then we have a take a is into this form. This clearly we have to find the what is the LCM of a these two 4 and 6. So, we can easily write into the this form. So, now determine the following permutation as even or odd. Now, you just said that is equal to 3. So, this is clearly is m is equal to 3. So, you have a even permutation, even number of 2 transposition, this is equal to even. So, this is giving you a odd number of 2 transposition, this is equal to 1, 2, 3, 4. 5 is odd, again is giving you a even number of transposition. Now, this is the even, this is odd, and this is giving a even, and this is even plus even, and even plus odd you have to give into the odd, and then you have a this is even, this is giving you a odd, and this is equal to odd. So, this is odd, this is also giving you a even. So, this means we can say simply by this the permutations can easily, if you take by way 1 5 1 3 is even, and for this we can say that 1 6 1 5 and 1 3 they are odd, and for this is clearly this is equal to even plus even. This is we getting odd cycle of a length even, and then we getting the odd number of a 2 transposition, and then again this is a cycle of a even length. We can take a odd number odd of a 2 transposition. So, clearly odd plus odd is equal to we getting the even. So, this is clearly we have to solve in the method of a this form. This is even, this is clearly odd, this is clearly even, this is odd, and this is clearly even, because that is a odd, and odd plus odd is equal to even. And now, next problem we have to discuss about suppose pi is a 6 cycle and theta is a 5 cycles. Now, determine the pi to the power 5 and theta to the power 4, pi inverse, and theta to the power minus 3, and pi to the power is even or odd. Now, because pi is a 6 cycle and theta is a 5 cycles, so pi is a 6 cycles means pi is equal to you have a odd permutation. So, pi is equal to odd number of 2 transposition, and then theta is equal to you have a even number of a 2 transposition. Now, odd to the power 5 you have a odd, e to the even to the power 4 is equal to so you have a odd to the power 5, and then you have a even to the power 4, and then inverse of a odd is equal to odd, and then you have a to power minus 3 of even to the power minus 3, and then you have a odd to the power 5 is there similarly. So, we just take a like this 5 cycles are even and 6 cycles are odd. So, pi is a odd and theta is even. So, number of 2 cycles are this of the form 5 odd, 4 even, 3 odd, 3 even, 5 odd. So, this means the same as the odd, even, odd, even, odd. Now, we have to, we just say that right, and this if you have a even plus odd, and this is equal to odd, even, and then this is equal to even, then odd and even is equal to odd. So, this means clearly this problem we have to write into clearly this is it. We have to show that theta pi to the power 5, theta to the power 4, and pi inverse and theta to the power minus 3, and pi to the power 5 is a odd permutation. Okay, now if we have another problem, let pi and theta being belongs to Sn, and then theta inverse pi inverse theta inverse and theta pi is an even permutation. This is again not a very difficult. We know that a permutation and its inverse are both even and both odd. So, if pi belongs to pi theta on, then the possibility of the numbers of 2 cycles in this, and then if you have a odd, even, odd, even, odd, odd, even, odd, even, and then we have to even, 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 and this in all the possible cases we have to getting the even. So in this case we simply say that because we know that the inverse of a permutation, its inverse are both even or both are odd. So agar if pi is even, then pi inverse is equal to even, pi is theta is even, then theta inverse is equal to even. So if we take a, this is both are odd, so this is possibility, then if is equal to even, then it is inverse and then odd, and similarly we have a even and this is odd, and then we have two possibility of this. So this all is this four possibilities are there, and in all the four possibilities we have to getting the all are the even, that is equal to even, this is also giving even, is also giving a even, is also giving a even. So in all the four cases we have to getting the this permutation should be even. So now I just take a another problem. Let pi and theta belongs to Sn, then theta pi is even if and only if theta and pi are both even or both odd. So this I already discussed. Let pi be a can be written as a product of a m2 cycles, and theta can be written as a product of a n2 cycles, and this is the juxtaposition of this two cycles can be written of theta pi as a product of a m plus n 2 cycles. Now observe that m plus n is even if and only if m and n both are even or both are odd. So we just write a product of these two cycles is m plus n. So m plus n is even, two cycles are even only in the case m or n both are even, and odd even both are odd. That is a proof is very trivially we can just say that. So I just take the last problem of today's lecture. I just we have a pi is equal to, we have a 1, 2, 3 and 1, 4, 5, and then we have to write the pi to the power 99 in a disjoint cycle form. Actually pi is not a disjoint, we have to first write pi as a disjoint form. So we have a pi is a disjoint form, we have to 1 and this is going to 4 and 4 goes to 4, 4 goes to 5 and 5 goes to 5. Now 5 goes to 1, then 1 goes to 2, 2 goes to 2 and 2 goes to, you have a 3, 3 goes to 3 and 3 goes to, you have a 1. So this means the disjoint cycle is a 1, 4, 5, 2, 3 clearly. So this is pi is equal to, we have to write into this form. So pi is a product of disjoint cycle, so 1, 4, 5, 2, 3. Now we have to calculate pi to the power 99. Now the 99 can be written in the form of a pi to the power 100, pi to the power minus 1, and then pi to the power 100 can be pi to the power 5 to the this, and then now you just see this is equal to 1, 2, 3, 4, 5, this is equal to odd, and so this means the permutation is equal to even. So clearly this pi to the power 5 ka square, and then we have to just say that pi to the power 5 to the power 20 and pi inverse, and that is a even permutation. So this is giving you a this is giving because this is order is this is equal to 5. So the pi to the power 5 is equal to, you have identity from here because there is a 1, 2, 3, 4, 5, order is equal to 5. So this is order is equal to 5 means we have a pi to the power 5 is equal to, we have a identity, and using the identity to power anything we have identity in pi inverse, then pi 99 is equal to pi inverse, and then pi inverse can be, we can easily calculate in from here. This is nothing but equal to 3, 2, 5, 4, 1 and this. So this is clearly, and then this in the cyclic notation we can write in the form of a 1, 3, 2, 5, 4. Or the inverse of cycle is also is calculating by this way, and this is a, and this is just is a also is a disjoint cycle of a. So we can calculate the pi of the pi to the power 99 is equal to, you have a 1, 3, 2, 5, 4, and this is the final answer of a this question. So, I have to stop today lectures here. Now, we have to complete this permutations part of this. In the next class, I have to discuss about the dihedral groups and symmetries of dihedrals of a triangular, and we have a rectangular forms also there. So, thank you for today lecture.